Hey, hello everyone. Thanks for listening to our session today. My name is Lu, and I'm the Director of Machine Learning Engineering at Restaurant Brands International. I'm excited to be presenting our work at Summit today. We're going to talk about our mobile order fast food recommendation service we built at Burger King. I'll start with our use case introduction, and then talk about our newly developed transformer cross-transformer model in details. And then Kai from Intel will talk about AI on big data and how we build together our distributed training pipeline using Ray on Spark. So let's start with our recommendation use case. So when we look at the fast food recommendation, right, click-through rate recommendation, it's similar, right, to the like non-fast food recommendation, right, which you typically see at e-commerce website. But it also has some like unique challenges there, right? So I think first is like in the fast food use case, we need to handle kind of different level of the product, right? So typically, like as you know, in the fast food restaurants, you can order things in a combo, right, which contains multiple items, or you can order things separately, right? So let's say a chicken nuggets, right? That's kind of like a la carte items, right? Which only including one. But if you order like a Whopper combo, that can including multiple items, right? So in this case, it's something our recommendation system needs to be considered, which is should we look at the parent level items, right, like a combo, or just individual items, right, like a la carte items. And the second thing is compatibility, right? So if you look at these two screenshots here, right, this is where we do recommendation in our mobile app. So it's very important, right? Whatever things we suggesting here needs to consider its compatibility with the other item customer already added to the cart, right? You don't want to recommend like another like large sandwich, right? When customer already have a Whopper combo in the cart, right? So compatibility is something a recommendation system needs to be handled, right? Kind of out of box. And also other things like location, time, weather awareness, right? So this is also very important in our use case because our restaurant is kind of spread across the whole nation, right? And a different location may serve something slightly different, right? And also given by different time, like during the breakfast hour, we really should just recommending breakfast items, right? And non-breakfast hour, we should do something different. So there's also a time component there, right? Needless to say, weather also plays important roles, right? When our customer orders food. So there are like tons of contextual feature needs to be considered here in our recommendation use case. And last thing is the guest checkout versus login, right? So this is pretty common in other use case too, but in our use case, right, if we consider guests differently than the login user, we kind of need to building like a different models, right, for each use case, which is a common approach, but we'll get into a second on how we approach this guest checkout versus login difference here. So here is a few approaches we try, right, in our recommendation use case. Collaborative filtering, right, is kind of like a traditional approach, right, very common being used. And wide and deep, right, neurocollaborative filtering, some deep learning based recommendation model also very popular. And we also look at some RNN based recommendation like session for rec, right, RNN latent cross, also very popular in other use case. And last, we look at some transformer based recommendation like behavior sequence transformer and Burful rec, right? But when we look at this kind of different approaches, we noticed some limitations, right, when using this, right? I think a couple of things here worth noting here. First is most of them, right, they all require like a user identifier, right? Which is fine in the login user case, but like in the our guest checkout use case, right, it fails to perform, right? It's kind of forcing us to figure out like slight different approach, right, to handle the guest checkout. And also the requirement of the user identifier makes us needs to manage a huge size of the user embedding, right? So like a brand like a Burger King has tons of the customer, right, visiting our app every day using the offers, right, place food orders. and they come and go, right? But for our recommendation system, in order to maintain those kind of user embedding, it's a huge size, right? And we have to do a lot of work just to make it work, the recommendation work in the production. So user embedding is also kind of a problem, right? And also is the challenge, right, to differentiate current session purchase, right, versus previous purchase history. That is also kind of hard to handle, right? Because if you look at the recommendation algorithm like neural collaborative filtering, it doesn't really allowing you to separate like the current sessions purchase, right, versus previous session. So let's say user previously purchased a Whopper, right? In the current session, if they haven't purchased Whopper, you probably want to recommend a Whopper. But if the Whopper is actually purchased in the current session, you probably want to do something different, right, to consider the compatibility. So I think the ability, right, to differentiate the current session purchase versus the previous purchase history is also very important, right? And last thing is the ability, right, to learn kind of complex context feature interactions, right? So I think in our case, right, we already mentioned things like location, time, like the weather, but like we also want to go a step beyond that, right? In our mobile case, right, which like we also want to look at anything like related to the user, right? Things like the device you're using, right? Like the carrier they're using, like and are they on tablet or on their mobile phone? So I think all those kind of features plays a role, right? When they interacting with our app and when they decide what food to purchase, right? So we want this recommendation algorithm to be able to consider those complex context feature interactions. So here we go. So we kind of come up with this kind of new recommendation solutions, right? So in here, we call that transformer cross transformer, which is essentially two transformers, right, side by side. And on the left side, right, we have this what we call is a sequence transformer. So what it does is it can take the item order sequence plus an optional purchase history as input, right? So this is quite interesting because for the purchase history, we actually not treating this as as same as the other items customer purchasing in the current sessions, right? So for the purchase history, we are doing average embeddings, right? So for all the items, right, user purchasing in the previous history sessions, right? So we kind of always put the purchase history in the position 1 of the transformer input. So model eventually can know, hey, like for the first input, right, that's not from the current session, but from the previous session, right? And this actually is very important, right? Because this allows us to use a same transformer to handle both use case, right? So for the user, we don't have a purchase history, that's fine. We're just gonna use a padding kind of a place at the first token space, right, to acting as the purchase history, right, which is empty. But for the user already have a purchase history, we're going to use all their previously purchased items, right, average it and put it in the first token space, right? So this sequence transformer can actually handle both use case, which is identify the users, right, and our guest checkout use case. And go to the right side, we're looking at the context transformer, right? So context transformer is another transformer, but it's dedicated being used here to learn our multiple context feature interactions, right? So things like location, weather, and time, and also user device, other user related features. It's a lot of context features, right? And the benefits we get, right, by using a transformer here is not only we can learn those individual features, right, but we can also using transformer architecture to learn each context features interactions, right? So that allows us to be able to learn from those complex context feature interactions, right? In a specific region, under specific weather, right? What customer are likely to buy, right? Just for example. And the way, right, we kind of combining both transformer into one model to generate a recommendation is that we're using this technique called the latent cross join training, right? So we are doing an element-wise product for both transformer outputs, and then we feed that into like a dense layer, right, in order to predict the next items, right, customer are likely to purchase, to click on, right? So this is kind of our model architecture. I think one thing, right, when we use deep learning, right, something worth to consider is there are just a tons of like parameter, right, for the model to learn, right? Even though we have a lot of like data, right, to train the model, but still, right, we are trying to optimize this model learning process, right? So typically, right, like in our previous iteration of the work, we are thinking, hey, like we can use a unique item identifier, right, to feed into the model to do the training, which works, right? But we also think, hey, just learning and embedding from the item unit identifier, which is just like a string, that is not that efficient, right? Like, why don't we, initialize this embedding, right, for the model to learn using something, this item already provided to us, right? So we actually look at that from the exact customer perspective, right? So we think when customer look at our item, right, customer probably look at from like two things, right? One is item description, right? So what is this, right? This is like 20-piece chicken nuggets, right? So it's self-explanatory, right? It's just 20-piece chicken nuggets. And also the image, right? Image also plays a huge factor, right? When customer select our food items, right? So so we're thinking from customer perspective, if they made purchase a decision, right, based on the description and image, we should do the same thing. We should have the model learn from the same thing, right? So we actually apply some pre-trained NLP and a computer vision model, right, to help, right, initialize our model embeddings, right? So the way we are doing here is we apply a pre-trained BERT model, right, to learn the item description, right? And we also apply a pre-trained ResNet models, right, to learn directly from the item image, right? And then because those pre-trained model has such like huge embedding size, it's a little bit too much, right? Also, we want to be able to extract, kind of do the transfer learning, right, on our own data set. So the way we handle that is once we concatenate, right, both embedding output, we feed into autoencoder, right? In our case, it's a variation autoencoder to compress the embedding, right, into a much dense layer, right? And then those the learned kind of a dense vector representing each item, we will use that as a initialized embedding layer, right, to train our transformer encoder. And this proven to be accelerate our model learning process by a lot, right? So model can already achieve a great result in the initial epoch training. So next, right, we kind of look at some comparison with some models we previously mentioned, right? So worth noting, one is the RNN latent cross, right? So this is a popular model Google has been using on its YouTube platform. And comparing to the RNN latent cross, I think our biggest change here is when we handle the context features, right? In the RNN latent cross paper, they just do a simple concatenations, right? But in our case, because we have so many different context features, so we actually apply a transformer, right, to do better feature extractions out of those context features. So that's kind of a main difference here. Also, we replacing the GRU layer with the transformer to accelerate the parallel training speed, right? And another thing worth noting here is the behavior sequence transformer, which is another popular model has been applied on Alibaba website. And for this model, we both use a transformer, but some key difference here is a behavior sequence transformer actually relies on a user identification as input, right? In our case, we do not, right? We kind of, like we described above, right? We use aggregated kind of history, purchase history, right, feeding into our sequence transformer to acting as to learn from the user's previous purchase history instead of requiring individual embedding size for each users, right, which really accelerated the online inference performance, and without the additional work that needs to be done there to manage the huge size of the and constantly changing user embedding space. So, and then we want to just talk about some online inference performance comparison, right? So we did some A/B testing our app, right? The control group, right? We're using the RN latent cross model, which is a very close, right, to the way our model works, right? So I think given by the inference speed difference here, we takes a little bit longer, right, comparing to the RN latent cross, which is understandable because our model has a lot more parameters, right, comparing to the latent cross due to we have two transformer here and multiple layers. But it's still workable, right, and it's still kind of definitely acceptable in our online recommendation use case. And also, it achieved a much superior result, right, comparing to the like TXT comparing to the RN latent cross, right? We look at both conversion and add-on sales gain, and respectively, right? TXT achieved 7.5% better conversions, right, and 4.7% better add-on sales, right, comparing to the RN latent cross during our production A/B test. And the last part I want to talk about is the model training architecture, right? So previously we were using kind of very typical, right, but a separate Yang cluster and a GPU cluster to train our model. And the issue with this approach is there are like two different clusters, right, as you see here, and multiple data pipelines in the middle, right, to be kind of managed and maintaining the production. It also takes a very long time, right, for the data, right, to be transferred between our HDFS and two different clusters, right? With the introduction of the Luyang Spark developed by Intel, Orca is going to talk about in a second, we achieved this new unified model training pipeline on the same Yang cluster, where we do data preprocessing, model training at the same space, right? So that's all on my side.
Okay, thanks Lou for sharing the recommendation use case and the TXT model used at Burger King. Since Burger King has enormous gas transaction data on their big data platforms, and it would be really essential and beneficial to build a unified system for the entire recommendation pipeline. So in the remaining part of this session, I will talk more about the technical details, how we build the pipeline use Ray on Apache Spark. Before that, I will give an overview of the work that Intel has been doing this year in enabling the latest AI technologies on big data. So in 2016, we open sourced our first project named BigDL, which is a distributed deep learning framework developed natively on top of Apache Spark. That is to say, deep learning applications written in BigDL are standard Spark applications and can directly run on existing Spark or Hadoop clusters without modifications to the cluster. We have also done lots of optimizations so that BigDL can achieve both outstanding performance and good scalability on CPU clusters. Later in 2018, we further open source Analytics Zoo, which is a unified data analytics and AI platform for distributed TensorFlow, Keras, and PyTorch. Analytics Zoo enables users to seamlessly scale end-to-end AI pipelines to distributed big data. So the figure on this page lists some of the key features of Analytics Zoo, and you can see Luyang Spark in this page is one of them, and I will talk about the details later. Besides, on top of Luyang Spark, we built the project Orca in Analytics Zoo to seamlessly scale out TensorFlow, PyTorch, and MXNet applications based on Spark and Ray. We built project Zouwu based on Ray2 and Luyang Spark for scalable time series analysis. And besides, Analytics Zoo provides cluster serving functionality for distributed real-time model serving and PPML for privacy-preserving data analytics and machine learning. So when developers want to build a data AI pipeline, normally they would go through these three steps. First of all, they will finish a prototype on their laptop using some sample data. And if the functionality looks good locally, they will do some experiment on clusters with some historical data. And if everything is fully tested, they will deploy the distributed data pipeline into the production environment. So the target of Analytics Zoo is to easily enable users to easily prototype the end-to-end pipelines that can directly apply AI models to big data. So when users do these 3 steps, we hope that they need almost zero code changes when they scale their application from laptop to a distributed cluster. Also, we support to users to seamlessly scale their application and seamlessly deploy on the production clusters, for example, Hadoop cluster or Kubernetes cluster. In addition, we make efforts to relieve users' burden by automating the process of applying machine learning to big data. So for Ray users, actually, if they want to apply their Ray applications to the Ray to the big data, they actually are facing quite a lot of challenges. First of all, in the production environment, normally the production data is stored and processed on big data clusters. However, there are many efforts required to directly deploy Ray applications to the existing Hadoop or Spark clusters. Secondly, it would be a concern and a challenge for PySpark and Ray users how to prepare the Python environment on each cluster node beforehand without modifying the current cluster. And last but not least, traditional approaches usually will set up 2 clusters for big data applications and AI applications separately. And this inevitably would bring the expensive data transfer overhead and additional efforts to manage separate systems and workflows in the production environment. So it would be great and time and cost saving to have a unified system to combine the data analytics and Ray applications into a single pipeline on a single cluster. So that's why we take the opportunities to do our work for Ray on Spark. Next, I will elaborate the implementation details of Ray on Spark and how Burger King uses Ray on Spark for the distributed TXT model training. So we developed Ray on Spark to seamlessly integrate Ray applications into Spark data processing pipelines. So as the Ray on Spark's name indicates, Ray on Spark runs Ray on top of PySpark on Burger King's Young cluster. So first of all, for the environment preparation, we leverage ContentPack and Young distributed cache to automatically package and distribute all the Python dependencies on the driver node across the cluster at runtime so that users do not need to install them on all nodes beforehand, and the cluster environment remains clean after the program exits. So in the Spark setting, as you may know, there is a Spark context object created on the Spark driver, and Burger King uses Spark to perform to load data, to perform data cleaning, ETL, and pre-processing tasks. Later, Ray on Spark would additionally create a Ray context object on the Spark driver as well, which utilizes the existing Spark context to launch Ray processes alongside Spark executors under the same cluster. As you can see in the figure, additionally, we create a Ray manager within each Spark executor to automatically shut down the Ray processes and release the corresponding resources after the Ray programs finish. So I think many of you may be familiar with RaySGD. RaySGD implements wrappers around TensorFlow and PyTorch to ease the deployment of data parallel distributed training. So if users directly use the native modules of TensorFlow or PyTorch for distributed training, they may go through rather complicated setup steps in the production environment, and RaySGD can relieve the efforts to some extent. So we adopt the idea and design of RaySGD for MXNet distributed training, and also additionally we make further work to make our implementation with Ray on Spark best fit the Spark data processing pipeline. So similar to RaySGD, we implement a lightweight shim layer around the native MXNet modules to automatically handle the distributed setup of MXNet under the Young cluster. And MXNet workers and parameter servers all run as Ray actors, and they communicate with each other through the distributed key value store natively provided by MXNet. So now in our implementation, we have Spark and Ray in the same cluster, and therefore the in-memory Spark IDDs or data frames can be directly streamed into Ray's Plasma object store, and each MXNet worker would take the local data partitions of the Spark IDD or data frame from its local Plasma object store for the model training. So in our implementation with Ray on Spark, we have all the data transfer stays in memory. So therefore, it should be more efficient, and it would be faster compared with saving to disk or even transferring between different clusters. Project Orca provides a user-friendly scikit-learn style estimator API for the distributed MXNet training. So based on Ray on Spark. So actually, for users, they don't need to go into the details of the Ray on Spark. They just need to import Orca libraries and invoke any Orca context, and we will do everything for you, including we will launch the Ray and Spark for you across the cluster. If you specify the class mode to be Yang, Ray and Spark would be launched across the Yang cluster, and we would prepare the runtime environment for you and distribute all the environment across the cluster. And when you call init Orca context, you can specify the number of nodes and the cores and memory per node to use for your application. So after the initialization, you can use Spark context to load data and do data processing, and to generate the Spark IDDs for training and validation. So the last step you need to do is to create an estimator. So in the train config, you can specify the number of MXNet workers and parameter servers to use. And for MXNet users, actually minimum code changes and learning efforts are needed if they want to scale their single node MXNet training script from to a big data cluster, as they can directly input MXNet model, loss, and matrix defined purely in MXNet when they create the estimator. So in Burger King's use case, we use the TXT model Lu described before, and since it is a next item prediction problem, we use the softmax cross entropy as the loss, and we use top 1, top 3 accuracies as matrices. So after creating the estimator, you can call estimator.fit to launch this distributed training under the same Yang cluster, and given the Spark IDDs and the user specified epochs and batch size. So after the program's finished, the Ray and Spark would be automatically shut down for you, and users do not worry about the cluster managing issues. So this is basically all the code you need to write for a distributed MXNet training pipeline, and this should be straightforward, and the entire pipeline runs on a single cluster. No data transfer is needed. So according to Lu previously, they use a separate GPU cluster dedicated for TXT model training, and a large portion of the time is spent on the data transfer between the two clusters, and also they need extra human labor to manage different workflows and different GPU cluster. So after switching to the solution based on Ray on Spark, the entire pipeline becomes more efficient, scalable, and easier to maintain. Such a solution has been deployed into Burger King's production environment to serve their customers, and it has been proven to be a good solution. Okay, so that's basically what we want to talk today. So as a wrap up, in this session, we share about the cooperation between Burger King and Intel for the mobile order CTR recommendation with Ray on Spark. We have jointly published a paper and a blog for our cooperation with the link shown here, and you may take a look at it if you wish later. And also for Ray on Spark, we have published a guest blog at Rice Lab to discuss the details, and you can take a look. As I previously mentioned, besides Ray on Spark and the cooperation with Burger King, we have done a lot of work for AutoML based on Ray 2 and Ray on Spark for time series analysis. And my colleague actually conducted a session last year in the Ray Summit to particularly talk about this, and you may take a look if you wish to build time series applications. So if you want to know more information about Analytics Zoo, you can go to our GitHub page, and most likely you will find other functionalities of Analytics Zoo be useful to your work. And if you have a GitHub account, don't hesitate to start us on GitHub page so that you can find us whenever you want, and we will give you timely help. Now, currently, we are working on a recommendation framework in Analytics Zoo, and we are also actively cooperating with other industrial customers for more use cases of Rayon Spark, and we will be glad to share our progress in the near future. So that's basically all the contents of this session, and thanks all for your participation, and hope that what we have talked about can arouse attention. So feel free to ask any questions, and thank you for your time, and have a good day.